Good morning. Today we are going to learn a different method of solving non-homogeneous problems. As with all examples you encountered so far, many of these methods have a limited application in the sense that the PDE, the boundary value problem, should have a specific form. Even in that case, sometimes the method is not guaranteed to work, but when it does, the PDE still needs to have a specific form and specific properties. We already dealt with non-homogeneous problems. I will remind you briefly how we handle them at this point, and I want to point out the limitation of that method. So today, basically, we're going to study an improvement of it, if you want, that deals with a specific situation in which what we learned so far doesn't work. So before I describe how what type of problems we're going to deal with, well, actually, I just mentioned you can take a moment to write down what I just wrote on the paper. So the method we are going to study in particular deals with non-homogeneous linear PDEs with a non-homogeneous term in this specific form, in a specific separated form, namely a function of t times a function of x. If you look carefully on how we dealt with the non-homogeneous problem so far, you would have noticed also from the previous homework that the non-homogeneous terms depended on x only. They were either constant or they depended on x only, and for good reasons, because otherwise that method we learned didn't work if the non-homogeneous term depended on t. So the method today we're going to learn, the method of variation of parameters, can handle this type of situation. So it's slightly more general. In the course of this method, we are going to use one type of ordinary differential equations you learn in the ODE class, in the ordinary differential equation class, namely the first order linear ODE. So I'm not going to spend too much time on describing how you solve that, how you come up with a formula. I'm going to just state it here and indicate the formula that gives the solution of such equation. There are actually various ways to solve these types of equations, but I'm going to provide the most direct way to solve them. So those of you who took 270, Math 270, the ODE class recently, you might remember this. A first order linear ODE, let's say in y of t, right, the dependent variable, let's call it y, and the independent variable t. So the standard form of a linear ODE, first order ODE, is y prime plus a of t y equals b of t. So any linear first order ODE can be written like this. So we can prove that the solution of this equation depends on two integrals, basically. So the first thing is to compute the antiderivative of a of t. Let's call that the antiderivative I1. And then the second integral is the integral of b of t e to the I1. So you do this first because you're going to need it in the second integral to solve the second integral. So with these two integrals, the formula for the solution is e to the minus I1 c plus I2. You don't have to memorize it, just write it down on a piece of paper, on a formula sheet, as I recommended to you to create some formula sheets that you can use quickly. Often we can write the solution without the parentheses because you will see in examples, if I eliminate the parentheses, often this term actually can be simplified in a nicer fashion. Normally I provide the formula in this form because if you have to memorize it, I find it easier to memorize this format, e to the minus I1, quantity c plus I2. But usually distribute the exponential because often this leads to a nicer format for the solution. And so let's do an example to refresh our memory with this equation. So suppose I want to solve y prime plus 2y equals e to the t. And according to the formula, I1 is the integral of 2 dt, which is 2t. And the second integral is the integral of e to the t because that's, okay, so A of t is going to be 2, B of t is e to the t, if you want to match it with the notation in the formula. So the second interval is e to the t, e to the I1, which is e to the 2t. Combine these exponentials, that gives me e to the 3t, and so the antiderivative is 1/3 e to the 3t. Don't bother to add now the concept of integration, that's built into the formula. So that's I1 and I2, and so the solution for the ODE is going to be e to the minus I1, so that's e to the minus 2t, quantity c plus I2, which is, I should have written from the beginning, which is c plus 1/3 e to the 3t. So if we distribute e to the minus 2t, then we have c to the minus 2t plus 1/3 e to the t, right? Minus 2t plus 3t gives me t. If you have an initial condition, of course, as with all boundary value problems, as with all the initial value problems, you can deal with it at the end. So let's say y of, in order to find the constancy, right? So let's say we also have y of 0 equals 1. Then we plug in 0 for t, and that gives me c equals 2/3. So the solution for the initial value problem becomes 2/3 e to the minus 2t plus 1/3 e to the t. So this is one example of a first order linear ODE. Again, this will pop up in one essential step in solving the non-homogeneous PDE with terms like this, as I mentioned in the title. If you need some refresher, you can go over there's a website actually that I posted on Blackboard with calculus and differential equations review sources, if you need to come up with some extra example. Or even better, since we have to be self-reliant right now with many things, another way to practice is to simply pick up different numbers here, just change this a little bit, put the equation in Wolfram alpha, and then do it by hand, and then you can check the answer, so you can see if you are right. And let's finish this part, and on the second part of the lecture, we're going to start with the type of problem we will deal with, and then give some interpretation, some physical interpretation, and then illustrate the method of variation of parameters. So we will go over a full example slowly to emphasize all the important steps, and then we're going to finish with some overall guidelines of how the method works. So stay tuned for the second part.